Well, welcome everyone. I'm glad that most of you could make it to this week, or at least these short courses this morning. This ought to be a very challenging and very interesting topic that we've decided to do. I have the pleasure of introducing the four topics that we chose. What we did was we tried to focus these courses on what we think is the major issue here. A lot of it has to do with science that you can get from telerobotics and from what we're doing right now on the actual surface. So I'm not going to go through too much of a giveaway of what we're doing, but so I want to introduce the first person. First one is my co-lead, Kip Hodges, and I have to read this because I've been instructed to. Not by Kip. After 23 years of faculty at MIT, Kip moved to Arizona State University in 2006 to become the founding director of the School of Earth and Space Exploration. Kip has done research in the Arctic, Western North America, Peru, and the Himalayan Tibetan orogenic system of India, Nepal, and Tibet. His laboratory products include development of a new laser analytical techniques for noble gas isotope geochemistry and the application of these and more traditional methods of geochronology to terrestrial and extraterrestrial problems. He is active in the development of new approaches to planetary field geology using human and robotic exploration strategies. And just on a side note, he has been a valid friend in putting this together, so I'd like to welcome Kip.
Hi everybody, welcome here. I'm Eileen's opening act today. So she's going to do a fantastic job talking about actually doing planetary field geology. I'm going to talk about actually doing field geology here on Earth and the sort of lessons that it might lend to us when we're thinking about how to think about new and exciting ways to do planetary field geology on other parts of the world. A lot of my engineering friends and even some of my geology friends have a tendency to believe that this is what it looks like to do field geology on Earth. And it's usually one person working by themselves. They may take some notes. They may be excited enough about new technologies that they might use things like digital compasses, and they might use GPS to locate themselves, like I'm doing here on this particular shot. But mainly what they're there to do is to look at small outcrops or look at outcrops in some detail and then collect a bunch of samples indicated by those sampling bags you see below with rock hammers. It's a very traditional way of doing things, and other than that little handheld device that I have, it's not very much different than somebody might have been doing field geology in the early 1800s. But it's a very, I wouldn't say sedentary, but a contemplative way of doing science. This is actually the kind of science I do. This is Everest from the north side from about 18,000 feet, 18,500 feet, something like that. And it's an extreme environment in which to do field geology, and we have to get around a tremendous amount in the field, have to have tremendous amounts of mobility. This is another mobility strategy in Peru, coming down the Cotahuasi River. Those of you who are at NASA might note the pressurized rover that we're using for this particular expedition. But it's a challenging thing to do this kind of field geology. And I think it helps us think very carefully about how we might do field geology on other surfaces. I want to get out of the way telling you my take on terrestrial field geology, that it's primarily an adaptive observational science. And I think that's very important when we think about making plans to do missions to other surfaces. It's one in which we have to make a decision on the rocks as we go, as we're doing the science, how to change the experiment. And so it's a difficult procedure in that regard compared to some other types of laboratory science or even observational science here on Earth. It relies on abductive and inductive reasoning, so it's a complicated process of trying to decide what the relationship is between rock types, and if you're interested in collecting samples, what kinds of samples you want to collect. We don't grab samples. We go out and collect them purposefully. It involves progressively disproving multiple working hypotheses, which is a concept that was brought to science actually by the geological community back in the early 1900s, with the notion of when you're in the field, you do not have one hypothesis that you're testing, you have many hypotheses, and you're trying to reduce the plausible alternatives for an explanation of a process. It benefits greatly from having varied perspectives, and it is not simply a matter of collecting samples. I mean, I think that's one thing that we have to think about very, very carefully. As important as it is to collect samples on planetary expeditions, that's actually sort of the last part of what you do when you're doing field geology. I want to illustrate what some of the complexities are in doing this kind of geology when you're thinking about it in terms of, is this mic working? Do you think it's working? Still? Testing? Now it's working. I hear that. Okay. So I wanted to start out with a little bit, sort of a thought experiment for you about how field geologists sort of actually go out in the field and do field work. And here's an example of a topographic map. I hope you can see it up there. It doesn't really matter what the contours look like, but the main thing is that there's one hill and a slope that comes down from that slope in particular. And so nowadays what we'll usually do is we'll usually use remote sensing data of one form or another, and we'll try to make some kind of a preliminary geologic map of an area before we go through. And for those of you who aren't familiar with geologic maps, I'm not going to go into much detail about them, but you'll note that all of these dots are contacts, and all of those contacts in there are dotted, and they're dotted because we don't really know they're there. We assume that they might be there based on the observations we make from the remote sensing data, but we don't really know they're there. And so if I'm a geologist and I go into that area to try and understand what the distribution of these rock types really are, I'll probably start at the highest point on this map. And so I might plan before I ever get into the field some kind of a traverse that I want to take, and maybe it looks like that, where number 1 is the place that I start, 2 is the place I go next, the dashed red lines in between are sort of generalized traverses about how I might want to go. So based on that map, I might create that kind of traverse in my mind, okay, before I ever went there. And you can think about this a little bit like these are the traverses that were planned out for the Apollo astronauts, for example. Okay, it's not much difference in that regard. But here's the biggest difference. The biggest difference is that when we get to that high point in that particular area, in point 1 in this case, there may be things we see that we did not see from the remote sensing data, and we will take advantage of opportunities, this sort of adaptive approach to field geology, to go from one of those localities to a locality that's as near to you as possible to sort of give you a sense of what that geology might be and allow you to work very much better when creating the map in particular. So in reality, I might go from 1 to 2 in this case, and then recognizing that there are other units that I had not seen before, farther down the hill toward station number 3, I might go there next. And then at that point, I have to make a question about where, I have to ask the question about where I might go next, and I'm going to take advantage of the route of least resistance. I'm going to contour around the hill, side contour around the hill, so my path is going to be substantially different than the path that I originally started with. And so it might go 3, 4, 5, and so on. And at that point, I could potentially get back on track with my original traverse, but I probably actually wouldn't. I would probably continue to contour around, go look at other outcrops like 6 and 7 and 8 that I might be interested in. And if I go through that entire process, I end up with a traverse map after the fact that looks something like the one on the left-hand side. And based on the observations I made, and perhaps the samples that I took and the things I looked at in Outcrop specifically, I wind up with a geologic map like the one that's on the right-hand side that's color-coded for different units. But what's important about this is that geologic map looks a lot different than the geologic map that I started with. Otherwise, why did I even bother to go out and do field geology in the first place? And the second thing is that the traverse I ended up taking is radically different than the traverse I planned before I started. And that is totally unlike the Apollo missions. Okay? It's a completely different way of doing field geology. So as I see it, the problem before us as we think about doing field geology on other planetary surfaces is that the goals and the activities for the most transformational scientific research that can be done by humans or their robotic agents on other planetary surfaces are the same as those as field geology on Earth. So field geology on Earth gives us a good place to think about how we want to do that in the future. But the problem is that the reliance of terrestrial field geology on novel technology has been extremely limited. We've not done a lot of good, hard work trying to integrate these kinds of new tools in the field geology that we do on Earth. And so I believe we are actually poorly prepared to take maximum advantage of new and emergent technologies to develop an advanced approach to planetary field geology. And so the question is, how do you rectify that? So to me, future field geology on other planets may permit few or no second chances. So that's a design constraint for us. I mean, honestly, we don't know how many opportunities we're going to have in the next many decades to go to specific exploration targets. So we're not going to have many second chances, and we've got to do as best we possibly can. It's not like we can go back out into the field next weekend. We'll require extreme efficiency in order to do that because of the cost of all consumables and the cost of health and many, many, many other things, just plain cost. It could be encumbered by technology if we're not careful. Those of us who teach field geology and are trying to use new tools, even like little handheld GPS sort of devices, all of us have stories about how it actually got in the way of teaching the science because we use those technologies, okay? So right now, the technical readiness level of those technologies for field geology is actually very poor. It slows us down a lot. So they could be enabled by technology. We at least hope that they would be, that would allow us to do things better and more efficiency. And I think that doing field geology on other planets well in the future is going to require collaborative, and I mean direct collaborative efforts among scientists, engineers, and astronaut explorers themselves. I don't think that any one of those groups is going to be able to pull that off. And the goal is to be better than Apollo. It's not to be like Apollo, only in different targets. It's to be better. So, one of the things we can think about that we'll probably talk about in the sessions this week is field observations with augmented reality. We may be able to do a lot more than we have been doing before if we can get those technologies to work and actually add to the process in the field. A second is using Telus Science as an exploration strategy. And what I mean by Telus Science is basically being there doing scientific work in near real time. So cognitively from the perspective of doing the work in near real time. And a third thing that I'm very excited about is the notion of virtual field geology. We can download our cognition to a particular planetary surface, but we can also upload the planetary surface to us. And so I think there are lots of opportunities in that regard as well. Whatever we do, for sure, we're going to be using a lot of robotics. We'll use robots as scouts, we'll use them as collaborators, and we'll use them as surrogates, as we do now in some cases. And these are going to permit autonomous or coordinated scientific activities with those agents, and it'll improve the scope, it'll minimize our risk as we go forward. We'll have better options for human surface mobility than we have had in the past, certainly than we had at Apollo, and we'll probably have better options for that mobility than we do right now when we're doing terrestrial field geology as well. I prefer this pressurized rover to the one that gets you wet, for example. And so how do you go forward with this? So number one, to me, is that we have to explore technology alternatives rather than just come up with new technologies and then take them out in the field and see if they work. The approach that I would take to this is to define and refine the science goal. I'd lead with science, as in the upper left-hand corner of this diagram. And the color coding on these diagrams is that sort of orange, burnt orange sort of a color is where I think that science input is absolutely critical, and the blue is when engineering input is absolutely critical. So I'd start with refining and defining science, and then I would move over to identifying plausible enabling technologies, right? So basically the technologies derive from the definition and the refinement of the science goals in particular. Then we build and we test those possible instruments on lab benches and to a certain extent in the field. But then finally, we get the scientists and the engineers back together to assess and refine those instruments specifically. You know, this is an instrument I can use. This is an instrument that will do me some good when I'm trying to do field work. And that feeds back into a refinement of the science goals again. And then we just continue going through this kind of a loop in particular until we have a set of tools that seem like they're going to be an effective set of tools. To make this work, we're going to have to do some basic training, I think. And the first kind of basic training is scientist basic training. Scientists have to understand the engineering and operational challenges of planetary field geology. I mean, I think it's
interesting that I've heard so many conversations among field geologists or planetary field geologists and engineers that sort of have this expectation that there will be a tricorder that they'll be able to use, somewhere, and it will be a very easy, interesting thing. And I think a lot of scientists, myself included, don't fully understand all of the constraints that are placed by those guiding principles of engineering and what's possible now or what might be possible in just a few years. The curriculum for that kind of training has to include the risks and the cost of planetary exploration. I think that's very important as we go through. It's not a blue sky kind of a situation. There are constraints. And the pedagogy has to emphasize optimization of activities to minimize risks and costs, like energy and oxygen consumption and all that sort of thing. On the other hand, the engineers need basic training too. So the first is that engineers have to understand the challenges of planetary field geology. It's not like a simple sortie that we plan ahead of time will do the trick. It's not like collect any old sample will do the trick. So the curriculum has to include scientific motivations and practical goals for planetary surface exploration so we feel like we're all in this together. And the pedagogy has to emphasize optimization of activities to maximize a scientific return, not just to, if we want to do scientific research on other planets and make that a fundamental goal rather than something we do in addition to other kinds of things, we have to figure out how to make the activities work in such a way that they optimize the scientific return. The other step that I think we need to do is I think we need to look at science operations, or what I'll call SciOps today, as a research problem, right? Not as something that we can just go out in the field and do this. We already know how to do the science, because I think we don't. So we have to treat science operations on planetary surfaces as a research domain rather than just something we already know how to do well and just need practice at it. We have to design, execute, and assess the results of integrated laboratory and field experiments in a meaningful way. So for example, if you say that it is an important thing to collect samples on a planetary surface so that we can come back here and run them, then you'd best know that the techniques that you use to collect them will actually give you samples that will give you important scientific results. And that's something that's missing in many of our planning structures today. So I think you have to integrate not just the collection of the samples, but the actual analysis of the samples and the evaluation of whether those were good samples. And we also have to focus experiments on technology-enabled adaptive problem solving, where the problems are defined by larger science goals in particular. So I would like to see all of that kind of science operations research be motivated by specific science goals. Do we know we have to collect samples for geochronology? If we do, then we best start doing geochronology in collaboration with the process of doing the science operations research. So when we start looking at planetary surfaces, and I'll show you a few views of Mars here, I want to give you a sense of what the problems are that when I look at these things, not as someone like Eileen who's involved in curiosity, I look at it as from the perspective of somebody in geology. What would I do if I were dealing with this on Earth? And if I see a landscape like Mount Sharp on Earth, what I'm looking for, I look at that as an extremely daunting enterprise. And I begin to think, where am I going to go with these traverses very quickly up those ranges so that I can get the best possible understanding of what's going on in an area? And you're limited by technology right now in the way you can do this, but if you have better mobility, if you have either astronauts acting virtually or you have robotic assets that'll be able to do it, the goal is to do very fast, rapid reconnaissance over a relatively large area if you want to understand this kind of a landscape moving forward. If you move down to outcrop scale science, there's a lot of things that we can say looking at an outcrop like this that invites questions that you might not have been able to see from orbit. And in this case, I think if you look closely, let's see if this, oh, it does work. So if you look closely, you'll see a lot of little white veins that are cutting across the rocks in this particular area, dominantly dark rock, white veins cutting across it. And that's a relationship that, as geologists, immediately piques our interest because we know there are two different generations of material in there, and we really want to know what the relationships are between that white material and the dark material. You can tell that from here. You don't need to have a photomicrograph of an area to be able to see that. You know where you want to look. You can target your research on that particular area. And what we need is we need to make sure that the engineers working on the problem, the scientists working on the problem, the astronauts who are actually going to do the work already have a sense of that, boom, as they go into the process. And then if you look at a much smaller kind of a much closer in kind of a thing, there are all kinds of questions that this asks. And a lot of them are process-related questions, like what's causing this kind of cross-bedding that you can see in those rocks up here. A lot of people in this room already know this, but it's interesting how many people don't think about these things that way. So it's going to require multi-perspective approaches and a change in the way you do science, a change in the science ops depending on what scale you're looking at a particular problem. And this is my favorite of all. This is a photograph from Mars of what is very clearly a sedimentary rock, okay? It's a combination of a lot of different rocks, a lot of different pebbles, different combinations in here. And just like on Earth, there is a wealth of information associated with that in terms of the age of the materials, the relationship among the materials. What was the history of this sedimentary rock after it was deposited? What does it tell you about the source region that you see? It's an amazing, amazing rock that you would make a very, very high priority target of collection if you were going to collect samples going into the future. So the way I would do science operations research is a little bit like that, like this. I would start out by designing an operations experiment. Here's a question that we want to retire. We want to understand more about the answer to this question with regard to doing scientific operations. And then I would go into a mode of working with engineers and scientists to define and refine the operations protocol in a particular example. Then I would next evaluate the efficiency. Is that protocol going to be fast? Is it going to be agile? Okay? Again, in collaboration with the scientists and the engineers. And then I would move forward to trying to evaluate the quality of the science return that we're getting back. And so in many cases, it means things like collecting the samples and going through the science return, figuring out whether it's high science return or low science return, and then put these two things, this evaluation of efficiency and the quality of the science return, back in the box and continue to optimize this until we feel we've got a good, stable system that's working well, and then finally go out and evaluate the experimental outcomes, both from the perspectives of engineering and the perspectives of science. Step 3, which I think is really important, is effective astronaut basic training. And here's a photograph of some training that Jose up here, we'll see him later on this week, sitting right over there. And Jose and I were working on with some of the last class of astronaut candidates in northern New Mexico a couple of years ago. And some of the things we were doing, most of the things we were doing with this exercise were classic traditional field geology. They're no different than I would use teaching graduate students and undergraduate students how to do field geology 30 years ago, okay? But that's what we were doing with the astronauts just a couple of years ago. I think we can do better than doing that kind of geology. So first, astronaut explorers, only some of whom might be geologists, must be schooled in the essentials of planetary field science, and they have to be schooled with the advanced technologies that we might be able to use. So that's why they need to be in this process of science operations development. The curriculum needs to include scientific context, field observation, instrument deployment, and sample collection, not just going out in the field and looking at samples in particular. The pedagogy has to emphasize the value of multiple perspectives and multiple working hypotheses going in. It's a fantastic way to think when you're doing field geology, and it's not a difficult thing for people to learn. And they need to understand the notion of doing on-the-fly problem solving. It's not just about collecting data, it's about solving problems on the field in real time. And a goal should be to educate them to contribute to science ops experiment as part of their preparation for future planetary surface research. Okay? Not just learn how to use it, but help learn how to develop it. And I think that many astronauts would be stoked for that. Right, Nick? Yes. Right, okay. So here are my takeaway messages for today. The first is, we are ill-prepared for optimal planetary field geology. We are not there yet. The second is that care has to be taken to avoid adding complexity just because we can. We have to add and not subtract as we move forward with technology. Because it is possible, I guarantee you, to subtract if you use technology in too cavalier a way. The effective preparations are going to require recursive efforts among scientists, engineers, and astronaut explorers. It has to be a recursive process. We cannot throw these ideas over the transom from one of us to the next, okay? We can't have engineers, here's my new technology, go out and try it. We can't have scientists say, here's my science goals, figure out some way to make me be able to do this. I think we can do better than that. And I also want to say that there's a great value for field geologists who only work on Earth to be involved in this process because of the feedback associated with it. I also think that right now we do field geology on Earth in an extremely rudimentary way. I mean, we go out, like I said, and we do it not much different than the way it was done in the early 1800s. A little bit of new technology, but that's about it. And so I think that we can begin to take the new enabling technologies that are built for, in a prototype sense, for field geology on other planetary surfaces, and we could interject those directly into field geology processes here on Earth. And that is the fastest way to make sure that we troubleshoot them, we get them working really, really well, and I personally think it could revolutionize terrestrial field geology. So with that, I'd rather have a conversation than continue to talk at you. So thank you very much for listening, and questions, answers, comments. Let's go.